搿么哪搿能样讲闲话，算是让我上课了咯。Okay, hello. Hello everyone. Welcome to the last lecture for Battlecode 2021. Today is the Friday of week 2, so this is going to be our last lecture. Just a couple of words of announcements to start with. We have the second sprint tournament coming up soon, early next week. So the second sprint tournament will be on next Tuesday. So what that means is the submission deadline for the next sprint tournament will be on Monday at 7 p.m. Eastern Time. This is, again, like last time, this will be a hard deadline. So please make sure you get your submissions in by 7 p.m. on the coming Monday. If you're late with your submission, unless you have any technical difficulty submitting, it will be very difficult for us to be able to include your bot. So please make sure you try to submit early to make sure you get your bots in on time. So that's sprint tournament coming up next week. Another announcement is that we are aware of an issue with the maps with zero influence enlightenment centers. That is getting fixed in the next release, and we will be releasing updated maps right after this lecture. So this will be happening. This will be happening very soon. Like the last lecture I ran, if you have any questions, feel free to just throw them in the Twitch chat. I will be watching that, and we'll be keeping an eye on anything there to answer those questions. Okay, so I guess from there we're going to move on to the lecture for today. So the main thing we're going to do for this lecture is we're going to sort of continue and extend on what we did last time. So last time we sort of looked at some pathfinding strategies and a bit of communication. What we're sort of going to do today is try to piece together perhaps a bit of a larger sort of a theme for a strategy. So if you were at office hours yesterday, we had 2 days ago we had a bit of a discussion about the sort of strategies that we may want to try. So we're going to try to perhaps formalize these a little bit today and maybe extend on it a little bit more. So we'll see what we can do. I see in the Twitch chat there's a question about the cow map. We will take another look into that as well, just prior to release. So I will take a note of that. Yeah, cool. So I suppose what we're going to start off with is we're going to take a look at sort of, we're going to start off with just taking a look at some other ideas for pathfinding, and then from there we'll move into sort of a general game plan sort of topic. So for pathfinding, last time, so you might remember last time we talked about some heuristic algorithms for bug finding. So we talked about the bug algorithms from the basic bug, which is also called bug 0, and we improved it to bug 1 and bug 2. And so today what we're going to do is we're going to look at perhaps some more exact forms of pathfinding, which may be a bit more bytecode costly, but these algorithms can be used for some more precise forms of pathfinding algorithms. So we're going to start off with the BFS algorithm, which perhaps some of you may have heard of before, and we're going to try to naturally extend that and see how we can arrive at the Dijkstra's algorithm, which can be used for pathfinding where not everything takes the same amount of time. And then finally, to make Dijkstra's algorithm a bit more bytecode friendly, we're going to bring this to Dial's algorithm. So this is what we're going to start off with today, and then after that we'll move to some of the more macro strategy planning ideas. Okay, so to start off with, we're going to look at breadth first search, which is what we call BFS. So BFS stands for breadth first search. And the idea for this, we touched on this very briefly last time. The idea for this is to really just explore everything, and explore your entire surroundings, and to discover what's around you, and to make the best decision you can given everything you know. So rather than doing something like bug, which sort of makes the locally best decision, what breadth first search tries to do is make the absolute best decision it can. And the idea is something like this. What we're going to do is we're going to keep a track of the exact distance that every square is away from our current location. So what this might look like is, for example, if you have a grid, and then let's say that you are in some location on that grid. So let's say that you are here in this circle. Then what we're going to do is, in a basic breadth first search, the idea is fairly simple actually. What we're going to say is, well, we know that this square is the only square, for example, that is a distance of 0 away from us, because the only way to be distance 0 away from yourself is to be at your current location. The next thing we do from there is we say, well, okay, what we're going to do now is we're going to find all the squares that are distance 1 away from our current location. And again, we're going to assume here, just for now, that again we're dealing with possibilities that are 0 or 1. And then we will relax this again a bit later once we move away from breadth-first search. But to do this, you will say, okay, you will take every location that is marked with a 0, like this orange square here. And what you're going to do is expand from that square, because you know that every square next to that square is at most 1 away from it. So you will do that, and you will get the ones in the 4 neighboring squares. And of course, you could keep on doing this. Actually, we should note that because you can move in all 8 directions, we actually get the ones in all 8 neighboring squares. And from there, of course, there may be some obstacles on the map. So you might get some squares which you're not allowed to walk through. So perhaps you have obstacles here. Then the next thing that will happen, you will expand, but ignore these 0 passability squares. So if I just add one more here, what we're going to get is we're going to get the 2s, which come out from the 1s. But we note that it's not always just sort of an expanding square coming out of the center, because once we get to the 3s, we can see that, well, because of that wall of obstacles, actually, I think I may need one more obstacle here. So if we just said that this square was also an obstacle, but once we get to the 3s, what we'll see is that we actually have another unreachable square. And so so this one square here, is a distance of 4 away. And so this is sort of the basic idea of doing a breadth-first search. And so this square is a distance of 4 away. And so this is sort of the idea of doing a breadth-first search, where you have a current location, and then you're able to expand out from it, given where you currently are. So that's sort of the conceptual idea of a breadth-first search. And if you were to implement it, it turns out that I suppose the simple way of implementing this doesn't actually require you to do too much work about thinking about where you were going to try to expand next. What you could actually do is you can notice that you can guarantee yourself that you will always find squares in the order of distance away from your current location. And what this will sort of end up looking like is you can use a queue data structure. So you can use a queue to help you keep track of the squares that you still need to expand. So what your queue will really do is you will have a queue, and then you have a queue. So you're going to have a queue called queue, and initially it's going to just contain your current location. And then the expanding phase of the BFS will essentially just say that while we have more squares to process, we're going to take the first location in the queue. So we're going to call that U for now. So we're going to call U as remove first from queue. And then simply, because we're now going to expand from U, we're going to say for each neighbor of U, we're going to say that if the distance from U plus 1 is less than the distance of that neighbor, which we'll just call n for now, then we just add the neighbor to queue and then update our distances. And this is sort of the basic idea of a breadth-first search. So U is the the first location in our queue. So if we were to simulate this, the queue is sort of like the set of squares that we haven't figured out yet. So let's say we remove all these numbers, and we're going to try to simulate this together. Alright, so let's say we start off with having only the 0 in the middle. And then the next thing that happens, so at the start, I'm going to use a highlighter to say that, so every highlighted square is the squares that are still in the queue. Now, what's going to happen is, on the first step, we're going to take U to be the first location in our queue, which will be that 0. And what this says is the next square we want to explore is that 0. And what we're going to do is we're going to take U to equal that square, and we're going to check all of its neighbors and then update our distances from there. So when we update our neighbors, what we're going to end up with is we're going to end up with all of these ones, which are neighboring the 0. From there, we have now removed the 0 from the queue, because that's the step that we do. We say U is removing the first item from the queue. But now we add every other square to this queue, because these are the squares that we just updated. So after updating it, we also add it to the queue. The key with this is, though, that I guess let's do one more. So let's suppose we now do one more iteration of this loop. We now remove the first location from this queue, and we didn't specify what order it was. So let's just say arbitrarily, let's say we found that this was the first location on our queue. And what will happen is we're going to do this, and then again we're going to update the squares around us, and we're going to get these 2's. And then finally we're going to add these 2's to the queue. The key here is to notice that these 2's are all behind all of the 1's in the queue. And so what that means is, you can't see some of the writing behind my camera. Thanks for pointing that out. Let me just move my camera a bit, if I can figure out how to do that. Is this better? Yep, awesome. So, but the key here is that all of the 1's come before all of the 2's in the queue. So what that means is we will always be processing everything in order, and we will sort of be able to do this expanding and find the distances for every square. And this is sort of the basic idea of doing a queue data structure. Okay, so are there any questions? Can I explain line 4? So I think line 4 is saying this line. So the idea here is to say, what this line is saying is distance of U is our current location. And if I say, and n we're denoting as this neighbor that we have. And the idea is, what we're trying to say is, what we're trying to say is, if the best way to get to that neighbor is via U, then we want to do this update. So I guess another way to think about it is, imagine if we didn't have this line, then what we would actually end up doing is, when we were exploring this 1, we would actually set every square around this 1 to a 2. And this is not what we want. What we actually want to say is, we want to check around this 1, and then for every square, such that the 2 is better than what was already there. So the 2 is not better than the 1 or the 0, but the 2 is better than these blank squares, which you could say initialize to infinite distance. But we know that the 2's are better than the blank squares, but the 2's aren't better than the 1's or the 0's. So what we want to do is we want to take every square such that our distance, which is 1, plus the extra distance of walking there, which is another 1. So this is going to take us to the 2. If the distance of 2 is an improvement on what was already there, then we want to expand there, which is by updating the distance and also adding that new square to the queue. Does that sort of make sense? There is a question about muckrakers self-empowering. Oh, I suppose you mean politicians self-empowering after sniping after a slander is sniped. I believe that so slanders are supposed to be a liability for you. Like they are your cost for gaining free influence, and it is your responsibility to try to protect them and not let them get sniped. And there is a penalty for getting sniped, which is that you may give your opponent a large gain. So it is a trade-off that you are making, in which you're taking a lot of influence now, but at the risk of losing more later. But yeah, so are there any other questions about the breadth first search? And if not, I'm going to take this to the next step and move it to a Dijkstra's algorithm. Okay, cool. So what Dijkstra's algorithm lets us do is move away from this 0-1 passability that we'd been assuming. Because sort of the problem we have here is that up to now, we have this +1 hard-coded in here because we're saying that everything is exactly 1 distance away from you. So what we want to do with Dijkstra's algorithm is be able to break away from that. And sadly, it's not as simple as just changing this +1 to, say, adding whatever the cooldown is for your move. Because what ends up happening is what we really rely on in this loop, and I sort of hinted at it before, is that our queue contains everything in order. So we contain the squares that are closer to you first, and the squares that are further away from you nearer to the end of the queue. So it wouldn't be as simple as changing this +1 to something else, because if we changed it, we don't actually have this guarantee anymore. But the fix for that is actually not as bad. So if I'm just going to copy this, and move it and then take another copy here, and what we're going to say is something along the lines of this. What we're going to say is now Q. This seems not the best color. Let's pick another color. Let's say Q. So we had before that Q is a Q, but now we're going to replace it with something called a priority queue. So a priority queue, and I just want to note here that a priority queue is something you can find in the Java collections. So I believe if you look in java.util.priorityQueue, this is something that is available, and you are able to get a priority queue straight out of the box and ready to use. But what the idea here is we're going to set queue to be a priority queue. And now, and what a priority queue does is say, well, instead of saying that we're just going to have a queue where the first person in is the first person out, or the last person in is the last person out, what a priority queue says is, I'm going to assign everyone a priority, and then the items with a higher priority get to leave the queue first, no matter when they were added. And then the items with a lower priority get to leave the queue later. You can think of it as sort of like, say, for example, being given a gold class ticket, or I suppose a silver class ticket to something, and those programs where they essentially say that if you have a gold class ticket, then no matter how late you arrive, they will wave you through to the front. And this is sort of the idea of a priority queue. Except here, what we can do is we can tell the priority queue that we're going to give everything a number, and we're going to tell it to take things out of the queue in that number, according to the order of that number. And what we're going to do is say, well, instead of removing the first from the queue, we're going to remove closest from the queue. And so what we're saying is the priority in our priority queue is exactly the distance from our current location. And finally, the only last change we have to make is say, instead of distance plus 1, we have to do distance plus whatever our cooldown is. And this is actually almost all the changes you need to make a Dijkstra's algorithm work. You do need to be careful that now, because of this, you will be updating squares more than once, because sometimes squares will get closer, and the distance values for squares will get closer and closer because you enter this this if statement many times. But when you do this, it is not too hard to get around that by adding, just in here, something where you say, if process U already, then skip. And this itself is what we call Dijkstra's algorithm. And that is a very good question. How efficient is this in terms of bytecode? And the answer is not the most efficient. And what we're going to do is we're going to now look at what we can do to make this better in terms of bytecode. It turns out that algorithmically, this is a very good algorithm. In terms of, if you are interested in, say, algorithmic complexity, then you could get this to be a very fast algorithm. But in terms of our bytecode usage, you might find that, say, for example, the priority queue is not the most bytecode efficient for us. And so our main goal is to find a way to do this Dijkstra's algorithm, but without this priority queue. And here is where Dial's algorithm comes in. So Dial's algorithm is, you could think of it as a variant of Dijkstra's algorithm. But what Dial's algorithm does is it assumes that your distances, it's not going to say that your distances are all 0 or 1. What it's going to say instead is all of your distances are reasonably small. Say like up to, say, perhaps 10, which is exactly what we have here, because every square you move increases your cooldown by up at most 10. Now, Dial's algorithm does also assume that all of your distances are whole numbers. So I'll just make a note here that Dial's algorithm assumes small whole number distances. But we can sort of approximate this behavior by taking all of our cooldowns and then, say, for example, rounding them off to the nearest whole number, because in the grand scheme of things, sort of the whole number itself gives you a fairly good estimate of where the cooldown puts you. And then from there, what the main idea is to, instead of using a priority queue, we're going to take advantage of the fact that we have small whole number distances to make our own pretend priority queue that does everything a priority queue does, but without the bytecode overhead of the actual inner workings of how a priority queue functions. The actual way we do this is actually not too complicated. The idea is we say, well, if all we need to do is just replace that priority queue, then let's think about what makes this priority queue special. We have a priority queue, and let's think about what we need it to do. We need it to be able to add a new location with some distance, and we needed to be able to remove location with smallest distance. There's actually one more thing that makes this priority queue special, which is that all of our whole number distances are small. And what does it mean for them to be small? Well, it means that in our Dijkstra's algorithm, when we remove the closest from Q, after we add this cooldown, it's actually not too far away from the distance of U. So what I mean by that is the final distance for our neighbor is still fairly close to our own distance. So it's not too far away. And to sort of formalize this, what we are guaranteed is that the amount of the difference between this distance and the smallest d, so sort of the difference between these two distances, is at most this small whole number. And so in our case, we know that this distance, the difference, is at most 10. And this is something we're going to be taking advantage of to make Dial's algorithm work for us. And so the idea for Dial's algorithm is we will just simply shake up this priority queue to take advantage of this small difference. And to do that, what we'll do is instead bring it back to some of our most simple data structures, which is an array. So if we just create a large array, and we're going to see what we can do with it. So let's say we have a large array. So this is an array. Let's see if we can draw that better. So we're going to have this array. And then what's going to happen is we're going to index into this array by distance. So this is distance 0, this is distance 1, this is distance 2, and so on. And then each time what we're going to do is say, well, okay, we're now processing squares with distance equals 0 to start with. We're going to start here. And then after processing squares, so essentially each cell in this array stores a list of locations. So inside each cell is a list of locations. And what we can simply do is say, we're going to process every square in here, and then each time we process a square, instead of adding it to the queue, we're going to add it to the right box it belongs in. And then after processing everything in here, we're going to move on and then start processing everything in distance equals 1. And after we finally finish processing everything in distance equals 1, we're also going to put everything in the right box and then move on to distance equals 2, and so on. So the idea here is that what we're able to do is take advantage of the fact that, well, because our distances are small, the key about the fact that the distances are small is that our array doesn't actually need to be that big. Because we can notice that, let's say, we eventually hit distance equals 11. Then by the time we hit distance equals 11, we know that everything behind us, say at d equals 0, is already empty, because our differences are at most 10. So in particular, what I mean by that is, what I really mean by that is you only need, say, to allocate 10 or 11 array cells, because the furthest you can reach from distance equals 11 is distance equals 21. And you can sort of just reuse these. So after you hit the end d equals 11, you can move d equals 12 back to the start, and then 13 here. And you can sort of cycle around this array and reuse the squares, because you know that everything you need is already empty, if that sort of makes sense. And by doing this, what we've sort of done is taken advantage of our small distances. We've created an array that behaves like a priority queue, which we can replace into here. And this sort of just gives us Dial's algorithm, which lets us run a shortest paths algorithm for small whole number distances without a priority queue. And this will be a lot more bytecode efficient than your Dijkstra's algorithm. So, any questions about Dial's algorithm so far? No? Okay. Cool. So, okay, yep. Yes, so each cell holds a list, that is right. Yep. So, with Dial's algorithm, it's actually the fundamental idea is the same as if we go back to BFS and Dijkstra's algorithm. So it's the same fundamental idea where we say we're going to start off at our own location, and then we're going to expand all the locations around us, and then we're going to expand all the locations around that, and then expand all the locations around that, and continue. So the fundamental idea for all three of these algorithms is always to say start at your current location and then sort of expand around you each time. And these three algorithms share this in common, and the only thing that makes them different is how they keep track of which squares you still need to expand, because this is sort of where the main weight of the algorithm is, which is to say knowing which square you want to expand next, because obviously if you expand them in the wrong order, let's say one very wrong order that you could do, for example, is just start with this 2 and then just expand it in this order, which is something you might end up doing if you have the wrong ordering. This is actually what a depth first search might do if you're interested. But the key behind all of these algorithms is to find a way to keep track of which squares you still need to expand and in the right order. And so what happens is the breadth first search handles this by saying we can just keep all of the squares we need in a queue, and because everything has distance either 0 or 1, it's either reachable or it's not reachable, then what will end up happening is, our queue will be able to keep track of these distances and make sure we expand everything in the right order. What Dijkstra's algorithm says is we're going to replace this queue with a priority queue, but we're going to keep the same fundamental idea. So we're going to keep the same loop, but we're going to use a priority queue instead. And the reason we use a priority queue is because we need to be able to handle these distances that aren't 0 or 1. So we can these possibilities that aren't 0 or 1. So we need to be able to handle all of these stranger distances. And so to do that, we use a priority queue. And then finally, in Dial's algorithm, which again uses the same fundamental idea of repeatedly expanding, but this time what we want to do is do away with that priority queue. And so the idea for how we do that is to find a different data structure that takes advantage of the structure of our problem. And the special thing we have about our problem is that our distances are all at most 10, and we probably don't mind too much about rounding them off to whole numbers. And what we can do here is we can replace our priority queue with an array, and now use this array, which simulates a priority queue, to do our Dicer's algorithm. And this is now what we call Dial's algorithm. Does that sort of answer your question? Okay, awesome. Cool. Okay, so that's sort of all of the pathfinding stuff that I have had planned for today. The next thing I sort of want to spend a bit of time talking about is some larger strategy ideas. And this is sort of spawning from the discussion that we had in the office hours session 2 days ago. That I think in terms of the strategy, it often helps to think of the strategy as, say, as in any game, you may be able to break it down into, say, an opening strategy, a mid-game strategy, and then closing it off with some sort of an end-game strategy. And sort of the first thing I want to say is that it's important to make sure that you play lots of scrimmages, because when you play scrimmages, you really get to see how your bot is going in production against other bots, because it is only by playing scrimmages that you're able to see more about what your bot is doing well, what your bot it might not be doing as well in, and really be able to evaluate those weaknesses and fine-tune your strategy to match those weaknesses. So if, say, for example, your slanderer units are often getting exposed by muckbreakers, then perhaps you want to reconsider your slanderer strategy, perhaps make less of them, or perhaps spend more time thinking about how you might want to protect them. And so the first thing I want to say is really make sure you play lots of scrims, because scrimmages are one of the best ways to see how your bot might fare against other bots, and definitely to see what your strengths and weaknesses are. There is a question about the scrimmage queue. We may consider rate limiting scrimmages. This is something that we are still thinking about, and we will. We don't have immediate plans to do that, but this may be something that we will implement at some point. But yes, what we would strongly encourage you to do is to play scrimmages, and definitely watch those replay files to find out what's good and what's not so good. Yes. So the next thing, though, is that in terms of your strategy, you want to think about, well, what you can do in terms of your opening, your mid game, and your end game. Well, the opening, some of the special things about this year's Battlecode is that, firstly, you don't actually have complete knowledge of the map. So unlike previous years where you might be given the map beforehand, or you might have more information about, say, even just the size of the map. Here, you have more of, well, you can only see the vicinity around you, and perhaps one of the first things you would want to do is really to explore the map and gain information about where everything is. So map exploration in the opening is perhaps one of the most important things you want to do. There's some questions, so I'll just get to those. Quickly. So would I recommend scrimming against bots on your own elo or bots near to the top? I think it would be good to do scrimmages against, say, bots where you can think you think that challenge you. So what I mean by that is bots that are, say, not too low and not too high, because you want to be scrimming in a range where you can see opportunities to improve. So what that would mean is potentially the bots that are around you, potentially the bots that are a bit above you, and it may also be a good idea to scrim the bots near the top as well, because the reason for that is by scrimming the bots near the top, you may see, for example, find some good new ideas for your own bot, or you might find new good ideas. You might find new defensive tactics against what the top bots are doing, and so I would recommend perhaps going for a range. So finding bots that challenge you, and also finding perhaps attempting to scrimmage some of the top bots as well, to have a chance at seeing if there's anything interesting, say, that they are doing. And definitely do not be afraid of ranked scrimmages. Of course, in the grand scheme of things, tournaments are indeed seeded by rank. However, we do run enough auto scrimmages that, say, there is no need to be, say, afraid of losing elo points when requesting extra scrimmages. And the other question about Dial's algorithm, about whether we have pseudocode for that. Yes, I am happy to release some pseudocode, say, into the Discord after the lecture for Dial's algorithm. But yes, so back to sort of the main overarching strategy ideas. I think what I was saying was that it might be good to think of the game as sort of your three phases, where you have an opening, you have a mid game, and you have sort of an end game. And where you sort of define these might depend on, say, for example, the state of the map, or like the state of where things are and where you think things are. It might depend on the round number, and I think some of the most common ones I've seen are to define these phases by round number. And the reason we use these phases is because we can use these to define different phases of our strategy and make our robots behave in different ways depending on how far into the game we currently are. And this is something we can detect because we do have the get round number function. And so what we sort of have is a map exploration phase, where we want to really get to know the map, find where the borders are of the map. So we want to be able to find the borders. We want to find the neutral we want to find all the enlightenment centers, whether they be our own or our opponents, because in either case, knowing where your opponent's enlightenment centers are lets you know where you want to start attacking, especially because enlightenment centers can't move. And the other thing is, if you find the neutral enlightenment centers, then you know where you're able to go and set up a new base. And it's important to note that because of the way that enlightenment centers gain passive influence once they're owned by a team, what this means is, as soon as you take control of an enlightenment center, it can take a lot more effort for your opponent to try to take it back. So going out there and capturing enlightenment centers is perhaps one of the underlying things you may want to do in your strategy. And so the first thing you want to do to be able to do that is to know where the enlightenment centers are. So the key there is to find borders, find enlightenment centers. If you're able to, you could even find information about the terrain. So in terms of the terrain, you have those squares that are high passability, low passability, and if you can sort of collect this information together, you might be able to get, if you're able to collect all this information together, you might be able to piece together enough of the map and actually run this through a larger breadth first search or a larger Dijkstra's or a larger Dial's algorithm, rather than doing one locally from just within your own bot. But this is sort of, but these are perhaps some of your main goals in the opening phase. In addition to that, of course, you have the goal of really boosting your economy. So really trying to increase your the amount of influence you can gain in the start, because the more influence you start off with, the more influence you're able to wield for the rest of the game. So the opening is it can actually be a fairly critical phase. In fact, we sort of end up with like a couple of, I suppose, main overarching strategies, where you have, say, the politician rush, where the idea is to try to take over the opponent enlightenment center right at the start of the game. And so you sort of, the idea of this strategy is to rush politicians to try to simultaneously explore the map and also aim directly at the opponent enlightenment center and take it over. Another strategy you'll see is this slanderer, if you want to call it a rush, I suppose, where you create a lot of slanderers with the objective of quickly boosting your economy to something very large, which is another strategy. And then the last one that's also very common is the muckraker rush, which is, I suppose, a direct counter to the slanderer rush, because the idea of this is to, on the one hand, find opponent slanderers, and perhaps also, if you're able, surround the opponent enlightenment center, because what that will mean is, if you surround it, it might no longer be able to build new units. And so there are these three interplaying strategies, and for you, you might find that one of these three might be more interesting than the other. Or you might come up with your own fourth strategy, or perhaps you might go for sort of a combination of these three, where you might perhaps create two politicians and a slanderer at the start of the game, and then use those as your starting units to really start your game off. But these are some of sort of the main opening strategies that have evolved so far, and sort of what you want to think about is which of these you think are the best for you, and also how you might want to defend against either of these, well, any of these three being played against you. So you want to think about what you would do if any of these three, if your opponent does any of these three, how you might want to detect that, and also how you might want to handle that. So whether that be, say, creating a politician as a sentinel if you see a politician coming at you, or whether that be creating a politician to deal with a muckraker coming at you, or hiding your slanderers if they do, or if you see for a long time nothing coming at you, perhaps you're doing a slander rush. So perhaps that's when you want to start sending muckrakers if nothing comes at you for a while. But these are just some of the ideas. When we go ahead to the mid game, some of your main goals here is, I suppose the mid game is where you sort of have some more involved combat between your units on either team. So the mid game would involve, say, being able to coordinate and pathfind to targets, and sort of This covers a lot of the things that we've been talking about. So with coordinating attack, you would want to be able to communicate where your targets are, and we've talked about how to do that using your 24 bits of communication. And you have your 14 bits of location and 10 more bits of arbitrary information that you're free to communicate. With your pathfinding, we've talked a lot about different ways of doing pathfinding. So for long distances, you might use a bug nav to sort of get close, and then once you're close, you might use a dials algorithm to find the best way to make the last few moves. And this will let you to go all the way to your targets. A very important thing here to think about is your micro strategy. So sort of what we've been talking about here is sort of the macro grand strategy that you're employing, but it also helps to think about exactly what your micro strategy is. So this involves how do you actually execute an attack. So let's say, like for example, if you have a politician really up close next to your opponents, you might want to empower it, but at the same time you want to be careful, because if it's surrounded with a lot of friendly politicians, a lot of the influence might end up being wasted because it's divided evenly amongst all of the units within your radius. So your micro strategy would involve things such as thinking about, well, how exactly do you arrange your units? Do you say, for example, keep a gap between your front line and all of your other units, so that if your front line needs to attack, they don't have to have any influence wasted by the units behind them? And these are sort of the parts of the micro strategy that you want to think about. Perhaps another thing you want to think about is exactly what is your formation when you move towards the opponent, because it would be very different to move towards your opponent as a steady stream of units as opposed to a swarm of units. So if you had 10 units, let's say you had 10 robots, it would be very different to send the 10 robots as a line of 10 compared to, say, a formation of 10. Where sort of if you have a formation, you might be able to more easily overwhelm your opponent. And so by overwhelming your opponent, you might have a better chance of doing an attack. So ways of doing this might include, say, assigning robots to groups, and then within each group having, say, for example, a group leader that makes decisions on what to do. So rather than having everything coordinated by an Enlightenment Center, you might instead have the Enlightenment Center assign robots to groups, and then each group leader sets its own flag, which can be read by all the units close enough to it. And then this will let you have group leaders that direct robots around in packs. But these are just a couple of ideas on how you might be able to coordinate an attack that lets you have groups of robots, say, attack, rather than individual robots all doing their own thing. But in the end, don't forget that your goal in the end is to have your votes. So what that means is, if in the middle of all of this strategy, you need to remember to reserve some of your influence for votes, and part of that might include adapting adapting the amount of influence you bid if you don't receive a vote. So what you would want to do is think about how much you would be willing to bid for each vote. But at the same time, rather than, say, for example, bidding a flat amount each time, you might want to notice when your bids work and when they don't, in order to determine just exactly how much influence you need to bid to be able to gain a vote instead of having your opponent win that bid. So you are able to see how many votes your team has, and so sort of having this information will let you sort of you can sort of think about, well, if you know, you can detect when your own votes succeed. And so sort of having this information will let you think about, well, how might I adapt my bidding strategy given my previous record to be able to take advantage of what we have and to be able to get more votes through than our opponent. And this might be something that you continually have running, even though I've listed it here in the end game, but it might be something that you have running throughout all three phases of the game. But these are just some overall general strategy notes that are good to think about. And if you are registered in the MIT class 6147 and you're taking this for credit, then one thing you can do, one of the ways you just want to note that one of the ways for you to gain credit in this class is to submit a 2 to 3 page strategy report. So this will be one of the ways for you and your team to pass the class, which is to submit a 2 to 3 page strategy report, which summarizes your analysis of this game, your strategy approaches, and what you think works, what you think doesn't work, and really just analyze what you think defines this game. And this is so sort of thinking about some things that we've just discussed here, perhaps some of your own novel analyses. So this is one of the ways for you to pass the class. And just a reminder that the other way to pass the class is to defeat the reference player. The reference player we will release. We will be releasing this next week. So the reference player will essentially be using some of the ideas that we have discussed so far, and we will be running it in the dev team. So to defeat, so the precise requirement to pass the class and defeat the reference player is you will be able to request scrimmages against the devs, and what you will need to do is you can request as many scrimmages as you want, but you need to win at least 7 out of 10 consecutive matches. So you can request as many scrimmages as you want, but out of 10 consecutive matches against the reference player, if you win at least 7 of them, you will have passed the class. Will the reference player be open sourced? I believe yes, we will be open sourcing the reference player, but we will have more details about the reference player once it is released. Yes, we will let you know when the reference player is released, and this is just a reminder of how to pass the class for credit. And other than that, just another reminder that we have, just reminding you again that we have the sprint tournament coming up soon. So the second sprint tournament will be on this Tuesday. So remember that the submission deadline for that is this Monday at 7 p.m. Eastern time, and we will be looking forward to seeing all of your bots and playing out the tournament. There was a question about whether this was the seeding tournament. Originally this was planned to be the seeding tournament. However, we've thought about this more, and we decided to replace the seeding tournament with a second sprint tournament because we believe that this will better achieve the purposes of what the tournaments are intended to be. I think we had a bit of a discussion about what the seeding tournament was for and how we used it, and we decided it wasn't as effective as we would have liked it to be. So it has been replaced with a second sprint tournament. And other than that, so this is the final lecture, but what we do have is we have the second seeding tournament coming up, and just a bit of a roadmap for what's coming up further down. So this Tuesday is the second sprint tournament, as we've mentioned a couple of times already. The week after will be our qualifying tournaments. So in our qualifying tournaments, you will these will be the tournaments that are the gateway to the final tournament. So our qualifying tournaments will select the top 12 US-based teams and the top 4 international teams. And from these qualifying tournaments, we will put together a final tournament of 16. In addition to that, we will also have the newbie and the high school tournaments. So the newbie tournament is for our first-time MIT competitors. So teams that consist entirely of first-time MIT students are eligible for the newbie tournament, which will also be run at around the same time as our qualifying tournaments, as well as our high school tournaments, which are for teams that are made up entirely of US-based high school students. And so these will all be happening not this week, but the week, so not next week, but the week after. And then finally, our final tournament will be occurring on a Saturday, and this will also be online, given the way things are. So the final tournament will be streamed online in, I believe, exactly 2 weeks. We are looking 2 weeks and 1 day. So we are looking at Saturday the 30th of January will be the date of our final tournament, which will be online. And so I encourage you to definitely all be there for the final tournament. But this is sort of the roadmap of where we are looking over the next few weeks. Other than that, yes, the pseudocode we will be releasing. I will release some pseudocode for Dystra's and Dial's algorithm in the Discord. So we won't have it right here on the stream, but yes, it will be in the Discord. And there was a bit of discussion about the politician empowering instead of after a muckraker buff. Let's move that discussion to the Discord, and we can talk about it more there instead of on a stream where I'm speaking to my laptop and reading the Twitch chat. So let's move that to the Discord, where we can have a more involved discussion there. So the strategy report is a team report that describes. So the strategy report is a team report that describes your team's analysis of the game and your strategy. And to submit a strategy report, we will ask that you. We will have more details about it, but we will most likely ask that you email it to us at battlecode@mit.edu. But yeah, so I suppose that will be that's all I have had planned for today, and I will see you all on the Discord. If you want to discuss more about the politicians and the muckrakers, I will be posting some pseudocode for Dial's algorithm there as well. And other than that, best of luck for the tournaments. Just a reminder that we have a submission deadline coming up soon, and best of luck in the sprint and the qualifiers, and all the best for the next few weeks.